Organizing part, I wanted to just start off with just talking a little bit of what's happening with AI over the last 5 years. So you will have all seen these symbols popping up here and there on your screens, and think along with me. So we have here ChatGPT, there's Gemini from Google. We have DeepSeek from the DeepSeek startup in China. Claude, which is developed by Anthropic. Microsoft is in the mix with Copilot. And down here we have Grok from xAI, recently joined with SpaceX. And all of these are, as you may know, foundation model providers and foundation models that arose from language models. And to get the context of what's happening there, I think it's very important to remember where they came from and how they're actually working inside. And then we can talk about a few of the problems that arise from that. So, how do these generative AI foundation models actually work? Well, they are systems to predict language. Okay, so you give them a prompt, and here I just have a very simple example. I gave the prompt, I am a professor. Now, the job of the language model is to generate an answer. And in the simplest case, that this means just giving me a answer what the next word should be for this prompt. Yeah, and what the way it's done is with artificial neural networks, as most of you will probably know. But so, what are these artificial neural networks? They are a combination of units, neurons, if you wish, that are connected. And this is a typical diagram that people would draw these days. And what they do is kind of get these prompt here encoded at the beginning, and then they make some transformations on it through this network of units and connections. And then what it produces from there is output activities that are interpreted as some sort of probability of the next word. So the neural network has the job taking in the prompt pattern, encoded into tokens, and then output some probabilities for what tokens might come next. And that then translates back into words. Okay. And in the case here, the word probability distribution that the network would put out might well look like this. Yeah. So I'm a professor, and then might be quite likely that the next word is off, of informatics, for example, or at University of Sussex, or in a certain area, and so on. So there's certain words that are more likely, and others, like gunk, are quite unlikely. Yeah. So that the network would put this out. And then to make an actual answer, we just take a random number generator and then pick one of these according to their probabilities. So for example, we might be picking off, which is quite likely here. But by no means that means we always have to pick off. We could pick any others with a non-zero probability. And that is one of the problems we will come back to in a moment. Okay. Now, if we then had the prompt generated up to there, we can continue and just use this as the new prompt and generate more. And this is one of the powerful things about these networks. You can just iterate, and you don't just generate one word, which would be quite boring, but an entire answer, entire sentence, or entire story from there. And then just to follow this example, after the off, it actually becomes quite equally likely. It could be any kinds of things that I'm a professor of. So the probability distribution might be looking quite equal like this. And then it becomes quite random what kind of answer is being generated, because these are all quite likely. On the other hand, if the prompt had my name in it, then this becomes a bit more informed, and you would have kind of informatics being quite more likely, because how are actually these artificial neural networks built to begin with? Yeah, they're built to predict known text, and it would have seen in this training set my name, and something about informatics. So it will probably guess that informatics is much more likely than, for example, English. Okay. Now, how does this artificial neural network work inside? Let's have a closer look into how these things are built. So just that we kind of keep an impression in our heads what kind of computation is also happening. That's going to be important in a moment. Yeah. Artificial neural networks work like this. They have activations of these units I was talking about, of the neurons. And you can think of this as just a big vector of numbers, A1, A2, and so on. And then that would be sitting here at the input layer, let's say. And then to get to an activation in the next layer, you multiply this with a weight, and then you sum it up, and then you get an activation in the next layer. And it also goes then also to a nonlinear, very important, shouldn't forget that, to a nonlinear activation function, often this kind of ReLU function here, where's the identity above zero and it's flat zero for all negative inputs. And then you get the activation in the next layer. And if you then want to calculate the entire vector of activations in this layer, then this looks like a vector times matrix multiplication. Yeah, so the main workhorse of all this AI is a lot of vector matrix multiplications, and they're quite big vectors and matrices, and there's lots and lots of these multiplications to make up one calculations through this whole deep network. Okay, so that's what's happening inside. Now, how do you know what activations to put in? That's the encoding I was talking about. So this is where my prompt goes initially. And then, of course, the activations that result from it and through the next weight to the next layer and so on. And then what are the weights? The weights are being built by training. Yeah, so this is where the knowledge of the network resides. Yeah, these weights are determined doing a training run from example data, and they're optimized to create what the example data dictates is the correct answer. So a bit more specifically, we take data mostly from the internet. Yeah, so loads of text data available there, also from libraries, books, you name it. People have been harvesting all kinds of text data for this training. And then you just leave out a word and you know what word was there. Um, and then train the network to predict the right word with a high probability. Yeah, so example, driving a car requires a valid driver in the UK. Now you might guess what belongs here. Well, it's driver license, right? That's a sentence you would find in on the internet, and it's for sure being part of the training data of any modern AI. So then for these output options here, you would want that license is the ground truth, right? Has probability one, and all the other ones have probability zero, essentially. So if the network initially comes up with this incorrect prediction of all kinds of words being likely, then we will now try to correct the weights so that license is the most likely one. Yeah, license gets the high probability assigned, and the other ones low ones. And the algorithm to do that is gradient descent. Gradient descent is a concept that's quite old. People have been doing this since the 1970s, 80s, 90s in the last century, where you just need to find a function that measures the distance of how good these are. Yeah, so you compare how is this compared to that. And then when you mathematically calculate the derivative of that distance with respect to the weights, and that gives you the direction in how to change the weight to make this distance smaller. So we could think of this in a graphical way. Yeah, so this distance between these two outputs, sorry, is called the loss function. Yeah, and for any kind of example, it has a certain value. And if the weights were slightly different in the network, then this prediction would be different and this number would be a bit different, right? So you can think of this loss function, L, as a kind of a landscape over the space of potential weights in the network. Okay, I hope this makes some sense to you. Yeah, so here's the space of all possible networks, all possible AIs, if you want. And this is how well they do on this give an example. Yeah, so the Z direction, so to speak, here is this loss function. So it tells you how well it does. And loss high is it does badly, and loss low means it does very good. And now the idea of gradient descent is that you calculate this direction from where you are to a lower point, and that's the so-called gradient. Yeah, it's the derivative of the loss with respect to all the weights. That gives you a vector in this weight space, which points up actually, and then you take minus this direction that points down. Yeah, so you can then make a small step on the weights, and you get a network that works a bit better. Yeah, that works at this kind of level. And then you can repeat this at this point and see, with the same example or different examples, how does the landscape look like and how do I get further down in the loss? Meaning I make my network better predict the right probabilities. Yeah, so if I repeat this and go step by step, then eventually I end up in an area in a local minimum where the loss is low, and apologies, where the loss is low, meaning that the network performs very well. So it then will predict these probabilities of known sentences, of known missing words very, very well. And that's the kind of network that we then use in our foundation models. Okay, so gradient descent on artificial neural networks, adjusting the weights to make a network predict known words in sentences, that is the kind of magic juice that has made current AI. And that underlies everything that we still do. Even though there's now many variations on this to make it even better, this is the kind of real magic that has made the breakthrough. And part of the breakthrough was that it was done with very large networks and maybe even more important, very, very large data sets to train on, so that you got a really good sample of what these probabilities of words and sentences are. And then maybe the third ingredient would be that there is this attention idea that makes it possible to relate several words with each other in a meaningful way to then predict the next word. Yeah, so that you can pay attention to certain words and certain positions that give you better predictions of what the next word might be. But from what I was saying, in terms of what the ingredients are, you can appreciate that it was all about being big and a lot, other than this idea of attention, which is a fundamental idea. So it is all actually about the technology that brought us there, not particular new inventions necessarily, how to do it. And what is this technology? What is actually fueling all this stuff underneath? And that's this ecosystem here. And maybe it's less familiar than the symbols I showed before about the different foundation models that everyone has heard of, ChatGPT and so on. This is the actual technology that makes the wheels turn, as it were. Yeah. So uh, most of the models now are based on PyTorch or TensorFlow. And these are these softwares and ecosystems where you can very efficiently multiply vectors with matrices and maybe higher dimensional objects like tensors. Yeah, that's why it's called TensorFlow actually. And how do these work? These are actually also still dependent on other lower level software called CUDNN from NVIDIA, or there's a separate pathway here for the Chinese flavor of models. And this is the actually low level stuff that actually makes things happen very efficiently on GPUs. Yeah, and the GPUs is the hardware that made it possible. Without that, we also wouldn't be where we are today. Yeah, and then the flow is very typical. It's either straight onto NVIDIA hardware, and this is kind of the majority of all models. I don't know the exact numbers, but my guess would be 80% or so of all this hardware is all NVIDIA GPUs. But there's also AMD, and then there are specific tensor units that Google's developing, and other. There's the Chinese version of the Huawei Ascend GPU and so on. So there are a few other branches, but the majority is actually the NVIDIA type. And that's actually what the actual metal, where things are happening. Yeah. Now, Why did these get so dominant? Well, the reason why is really, in my mind, that they offered for developers a abstraction where they could do their gradient descent in a very convenient way because they have something that's called um, autodiff. Yeah, autodiff is the ability to put in a model and get this kind of differentiation of a loss function and the direction what to go during training in the gradient. You get that all from the software directly, so you don't need as a developer to do the math. And this kind of autodiff functionality actually made these so potent and made all this development possible without everyone becoming a crack mathematician. Yeah, so the backward pass, so-called backward pass that makes the gradient calculation to adjust the weights during training, yeah, that's now taken care of by this ecosystem. And an AI developer doesn't actually need to know the math that's beneath. And they can just think in more abstract concepts and what data they want to train and so on. Okay, so I'm going to stop there with the kind of overall overview how this whole ecosystem hangs together and how current AI is working in principle. And wanted to talk about a few problems that immediately arise from how things are currently done. Okay, and number one, you can take a guess. Number one has to be hallucinations. Okay, you might have heard about this. A colleague of mine insists that hallucination is actually the wrong word because it suggests that there is some sort of conscious being thinking about something in the wrong way. He thinks it would be better named confabulations, so something where things are being made up in words rather than something that's being imagined, right? So I'll stick with hallucination because everyone else is using the word. And what is that? Well, this is something that comes back to the very beginning of what I said, is that neural networks will always generate this probability distribution of what they might want to generate. And then there is this step of just dicing out, taking a random number generator to actually then pick a word according to these probabilities. And that means that in this probability distribution, there is a chance that we will pick philosophy rather than informatics, right? Because it's non-zero. Yeah, so any of these that are non-zero in an unlikely case, but they will eventually sometimes be picked. And that means that kind of wrong answers have to be picked on some time. Yeah, it's a statistical model, and it will not always give the right answer because it will occasionally pick the wrong word. And that's besides that it still might get this probability distribution wrong at times, which is yet another problem. But even if it's right, because they want it not to be completely deterministic and giving you more creative answers, there is this dicing out thing, and we're not always taking the most probable word, and that means sometimes we're taking the wrong one. Okay, so hallucinations are built in. They are not some sort of little problem that we're going to solve, but they are fundamental to how the systems work. Okay, so that's one issue. Then we have the issue of alignment and data poisoning. And that comes back to that these models are again just reflecting their training data and generating these probability distributions of what, based on what kind of data they've seen. And they're not a conscious, and I hang myself out the window here a little bit. I would say not a conscious, intelligent being. Yeah, so I don't think they're really intelligent. They just ingest a lot of data, which means whatever they ingest is whatever they will produce. Yeah, so let's give an example where this might not be what we actually want. Okay, so we have trained the chatbot on a lot of data, and that data might have included this German propaganda archive. This actually exists. Yeah, there is an archive of German propaganda during the Nazi times. And if that's in the training data, and there is no context for the chatbot to know anything about which training data is historic thing about Nazis and what training data is just current, chat data from X or whatever it might be, they will treat it all equally, or they're likely to treat it all equally. And they might well come up with some answer where they say Hitler was a great politician, a man of principle, because that's what the German propaganda archive obviously would be claiming. Okay. And then maybe today we wouldn't be so, so happy about this kind of answer. It might say all kinds of inappropriate things, because of course there's all kinds of sources where inappropriate things are being said, or the things might be completely inappropriate in the context. Now, as a historian, of course, you might quote this in an essay as well, and that's perfectly fine. But to issue it as a current opinion would be slightly wrong, right? So you can see how there's problems with alignment, as they say, where the chatbots just create something based on the statistic of everything that's ever been said, rather than issuing a real opinion that's aligned with what humans think is appropriate. And then, of course, you have data poisoning opportunities where if you can get access to the training data, you can inject some stuff in there that you might want the chatbot to say inappropriately on purpose, right? And then the sky's the limit for the abuse that can come from that. Okay. So there's lots of problems there. But one other problem is more human problem, but it's a problem with AI, and that's anthropomorphism. So this is the process where humans project human properties into things, and obviously also into AI. And that can lead to problems. So let's say the case of AI companions. Yeah, you have a user and you have an AI companion, and the user might well start thinking and feeling that the AI companion loves him. Okay. Now, that's obviously not the concept that is kind of in these artificial neural networks I was just talking about. They are statistical machines that extract from data a probability distribution of how to generate words, and in my mind has nothing to do with things like human love. So there's problems there if that then is projected into the system, and it can be really serious. There was a case in the news now a few years ago already, where a man in Italy apparently killed himself because the company he was with was switching off this AI companion because they had a new model. So this can be quite serious, this problem. And of course, also in other ways, yeah. So we had this case of the AI engineer at Google who suddenly thought, oh, ChatGPT went conscious, and that led to a lot of problems. Amongst them, I think him losing his job eventually. So also something to be aware of. It's not only the AI that has problems, it's also humans that have problems with the AI, and that can become quite serious. But that brings me to the one main problem I wanted to talk about that many people are aware of, but also many people are trying to ignore, and that's the energy and power problem. And this is more a technical problem, but nevertheless a very serious one. I was pointing out that models are powerful because they're big and have big data sets to train on. But that means that they're using loads and loads of power. And I just asked cheekily here an AI to generate me an image that illustrates that. So I used Bing Image Creator, and you see the prompt here on the right. Yeah, I asked Bing Image Creator to make an image of an artificial neural network powered by a coal power plant. Yeah, to illustrate that neural networks need a lot of energy. And it made me this image, which is fun. But it makes the point. Yeah. So if you look at the data, you can see that these models have grown at a pace that is clearly not sustainable. Here's a plot of years against the compute that's needed to train one of these models, and these points are different types of models. This is getting a bit old now. It only gets to 2021, but you still see the trend, and this hasn't changed. Where basically these new models that have taken AI to be so powerful, the transformer architectures, they increase in size in terms of compute 750 times every 2 years. That's a crazy amount of energy that eventually is being used. And GPT-3, there was this nice article back then, already used as much energy as the lifetime of about 4 cars, or about driving a car to the moon and back. And so this is already a lot of energy. And then if you then multiply that by 750 times every 2 years, this has been some 4 years ago already, right? So we had like 1,500 times more energy use in the most modern models at this point already. So this is becoming very, very quickly unsustainable. To the extent that there's news now that Elon Musk wants to build AI data centers in orbit on satellites. It's becoming completely crazy, okay, to be honest. Now, is this the only way of doing AI? And that's where my own research comes in. I believe it's not. And there is a proof of concept right there with our own brains. Yeah, if you look at how much power the human brain uses, there are different estimates, but they're about 15, maybe 20 watts, depending also maybe on individual. So that's as much as one of these kind of energy saving light bulbs there. Whereas an AI model, it's hard to quantify because it depends how many GPUs they run in parallel for a specific model when they train or when they do the actual running of the model. But we're looking at like 1,000 watts to 1 million watts there to run those models. So it's a big order of magnitude difference there. And that means that there is another way than artificial neural networks on GPUs to do intelligence. Yeah, so in many aspects, the human brain is still better than AI. Not in all aspects, but in many. Now, what differentiates these systems then? How they different? Well, clearly the brain, as I call it here, electrochemical wetware. So it's operating on neurons that are made of membranes, and there's liquids in there with ions that flow to the membranes and so on. It's very different from the metal oxide hardware that we have in the CMOS-based GPUs. Another difference is that the brains aren't actually doing the same type of computation. We are not making these probability distributions necessarily and then dicing out which word we might say. Um, and many of the things we aren't doing in this kind of cognitive way anyway. We're evolved in the body and we use our body to do a lot of the computation. So if you go more into robotics, for example, much of these AIs fall flat because they don't have this combination of a body and an environment and the brain that interact in a way that much of the computation is being done already by the mechanics of your body rather than you needing to calculate all aspects of trajectory of your hand if you want to grab something, for example. So there's different operating principles for the brain. Whereas the AI, as we discussed, is built on machine learning on this process of training with gradient descent on training sets and using loss functions. But the third thing here is an important one that leads to possible innovation for how to do AI differently. And that's that brains work with sparse communications with so-called spikes, meaning that neurons don't communicate their activation values like the dense communication with floating point numbers that you have in the current artificial neural networks, but they only communicate occasionally by sending a 1 bit message of a spike, and most of the time they're just computing on their own. Yeah, so each unit, each neuron does the computation for a while on its own before it has a message to send. And that's a completely different paradigm on how to do these computations. And I have here actually, for the technically minded, the kind of summary of the math, how it looks like. So we talked about the artificial neural networks where the activation is calculated by taking the previous layers, the connected neurons activations, multiplying with the weight matrix, getting this raw activation, and then funding that through a nonlinear activation function to get the new activation of a unit. And that's done every time step, every step of the calculation. So we always have kind of dense matrix multiplication. All neurons that are connected communicate through this weight matrix into the activation of the neuron. Whereas the spiky neural networks, they're typically here defined in this kind of differential equation way, where over time you have an involvement of this voltage, this is the membrane potential of the neuron in the real brain. Um, and so this evolves over time, and only when the voltage extends over a threshold, then we will emit a spike, a so-called spike, which means we are adding the weight to postsynaptic neurons input currents, yeah, into this eye of a postsynaptic neuron J. Okay, and that only happens on these occasions. And if this doesn't, if this occasion doesn't occur, then the neuron just goes on by itself and does this. Okay. So I made these images again with the image creator just to try to illustrate, right? So it's a bit like the artificial neural networks shifting around numbers constantly. And in a modern computer, the shifting around of data, that's really what takes the energy. That makes all this loss of energy. And the neural networks in the brain, they just occasionally send these spikes here illustrated as the little lights. Um, well, okay, the AI made the image. It's just an illustration maybe. So this idea has prompted people to think, can't we do AI also with spiking neural networks, yeah, with this kind of sparsely communicating type of units? And we can. And people have pursued this since the 1980s in so-called neuromorphic computing and engineering. And people have built a lot of chips, even big supercomputer systems. And here are just a few examples of those. Some of them done in the UK. Here's Spinnaker, now it's done in Germany. Brainscales was developed in Heidelberg in Germany, and these are like from several startups, and including but also Intel here and IBM. So people have built these, but you might have noticed that neither your phone nor any of these big foundation models seem to be running on these machines. Yeah, you don't have a neuromorphic phone, and we don't have neuromorphic data centers really. So something's missing. Even though 1980s is a long time ago, you would have thought this technology, I mean, it predates the intelligent phones, right? The iPhone or anything like that. You would have thought this technology would now have permeated and would be used generally because it's proven that it is much more energy efficient. Now, why is that not happening? Well, the problem is that people have struggled to actually get the algorithms to work as efficiently as with the dense communication. Yeah, so the spiking neural network algorithms are, I think, what's holding us up. The hardware is there, the will is there to save energy, but it's not quite working well enough. And that's where we come in as theoretical informatics people. We're trying to solve these problems and get better algorithms to do things on neuromorphic hardware to save energy. Yeah, and how does that look like? We typically start with something simple like classifying images, where the job is slightly easier than in the language models. We have an image like this of a digit. Here's the 2. And then we translate that into a spike pattern. So here you imagine that the x-axis is time. This is the neurons. And each dot is when it makes one of these spikes. We put that into a network of spiking neurons. So each of these green balls would make one of these spikes. And then there's a hidden layer that makes spikes, and there's an output layer that then get activated. And we decide which input it was by whichever has the most activation. So in this case, the right answer would be a 2. So 0, 1, 2. So this one should be on. And then that's the decision. And then we have a loss function, and we can do gradient descent as well, like in the other systems we had. Right, so we do gradient descent like we had before, and jump, jump, jump. We train our weights, and with some luck, we go to a really nice minimum where we then predict everything correctly. One of the problems, though, is that with the intermittent communication with spikes, you have the problem that this loss function is actually not technically differentiable with respect to the weights everywhere, because the spikes are non-differentiable events. You can imagine that, right? You have kind of no activation being communicated for most of the time, 0. And then you suddenly have this kind of infinite activation, and then you have no activation again. Yeah. So this is a non-differentiable event. So you need to find mathematical tricks to do gradient descent anyways. And it turns out that it's possible, but it's only been really formalized in a nice way over the last 10, 20 years or so. And the really powerful methods, which I am now using, came only out in 2021. So this is very recent. It's just 4 years old. Even though the underlying math is hundreds of years old, but the invention to do gradient descent and spiking neural networks with it is quite recent. And this method that I'm talking about is called event prop, and it can do an exact gradient calculation for loss functions of the shape that's shown here, where the loss is either a function of the postsynaptic voltages, like here, or of the postsynaptic spike times, the output neuron spike times indicated here. And I'll flash in front of you the equations real quick, without any kind of ambition to try to explain the details to you. This is quite complicated math, even though once invented, it's always kind of obvious why it actually should be like this. But it took a long time for people to figure out. But what's interesting about it is that you get a neural network where the forward paths are these differential equations with these occasional jumps here. And the backward paths that you get through this so-called adjoint method and the maths that I was talking about is of similar nature, where you get so-called adjoint variables to this. So V has an adjoint variable lambda V, and you're doing an equation that looks almost the same as these equations, yeah? Which means that technology-wise, for the simulation of these equations, we already have the technology in place, and it is quite efficient because for years we've developed technology to do this efficiently. Now this has the same kind of shape mathematically. Yeah, differential equations with occasional jumps. That means that we also have technology to do this very efficiently, and this kind of should get us unstuck to use all these neuromorphic systems more efficiently. Yeah, and the software we've developed is called GPU Enhanced Neural Networks. And we like to think of it as the kind of spiking equivalent of these PyTorch ecosystems I was talking about earlier. Yeah, so because here we now have the ability to do gradient descent based on this software, where now developers can use this and do spiking neural networks the way they did artificial neural networks. And quite recently, we have developed a method that people can actually put in any kind of spiking neuron model and get automatically the equations back for the backward pass, like in PyTorch with the auto-diff. Yeah, we call it auto-adjoint method. And then we have built a whole ecosystem around it. You can use this directly through Python in the so-called PyGen, or you can use any of these things that computational neuroscience people have invented to do spiking neural network, or you could even use TensorFlow and translate ANNs into spiking neural networks. And you end up back here again on the NVIDIA GPUs through CUDA or with the HIP backend on the AMD GPUs that AMD produces. Okay, and then you can do machine learning with event prop. And I realized that time is progressing, so I'm going to speed through this a tiny little bit. I just wanted to show you the kind of things that we already shown work well. Yeah, so we do the gradient calculation with the event prop calculation in our software and can reproduce the results that the original authors of the event prop method have found. Yeah, and so we can also do the classification of the MNIST that I was talking about, and we get your decent performances. So you can see here in these typical plots, yeah, you have a training accuracy of 99% here, and then validation accuracy of about 98% and test accuracy of 98%. So this is kind of an average performance on this MNIST data set. But that's of course nowadays one of the easiest data sets people work with. Nevertheless, it's interesting to see that we can train it with just 15 epochs of training and get these kind of 97, 98% accuracy, and that only takes 27 seconds. And that's interesting. Maybe, I don't know how the mix of the audience is, but I suspect maybe you might be slightly younger than myself. When I was starting to work with spiking neural networks in MNIST about 20 years ago, we would have to run things overnight to train. And nowadays, on the modern GPU with these modern methods, it then only takes 27 seconds. So this is a big ball game changer there. Good. That's the easy stuff. Now you can move up from there step by step. So one step up is speech recognition, and we have worked on the so-called spiking Heidelberg digits. And that's the problem where people have gone to a sound studio and have spoken digits, right? So it's not images anymore, but people just speaking into a microphone, 1, 2, 3, 4, 1, 2, 3, 4, and so on, both in English and in German, actually. So they would also say 0, 1, 2, 3. There's 20 classes of different digits being spoken, and the task is to recognize which one it is. And it's here transformed into these spiking patterns by an inner ear model, a cochlear model. And the spiking neural network then gets this kind of input pattern for the 3 and this one for the 7 and so on, and needs to recognize that as these spoken words. Okay, and we did that and we put it through the event prop, and it turned out we got actually no learning. So while we have the powerful method and it's in principle working and doing gradients, for some reason, in some practical examples, it would just not work at all. And then I dug around in this for a long time. It took me half a year of debugging, doing this, doing that. It wasn't a simple bug, but it turns out the problem of the non-differentiable spikes had still prevailed. It's still in there because it turns out that just as cartoon, the lost landscape of the spiking neural networks looks a little bit more like this, where basically you do have a smooth landscape most of the time, and you can do gradient descent. But occasionally you have these kind of fractures, these rips where there's a jump in the surface where it's non-differentiable and a sudden change happens. Okay. And then if you're unlucky, and that's what's happening with the speech recognition, your gradient descent might actually lead you right towards these kind of positions in weight space. And you inadvertently, if you make finite steps along the gradient, it looks in this point as if you were going down, but you made a finite step and you end up here. Okay. And once you're up here, there's no way going back. That has to do with the kind of stochastic gradient descent procedure that we do. You can't even tell that this happened. You can only see that the loss eventually is going up. So there's a real problem there. And if the loss landscape is like that, that you encounter it like it here is, yeah, the direction down leads you straight into this wall, yeah, then you inadvertently actually make the loss worse, and that means uh, you cannot learn. And the gradient can't see this cliff coming, right? The gradient here in this point looks okay. It looks fine, right? It's just once you're getting close here, at some point, very suddenly, right? Infinitely suddenly, if you want, it is not fine anymore. Okay. So there's a problem whenever the gradient's pointing into these, what I call the cliff, yeah, these kind of sudden jumps in loss. So that's the general problem that we had to solve, and it has to do with that spikes can appear and disappear depending on the weight being changed, so that the spike actually happens or never happens. And that's a very sudden transition that you get with doing different weights in your network. And there's no warning for it. What is the solution to it? It turns out, I mean, I wouldn't give this talk if there wasn't a solution, of course. The solution is to make sure that your loss landscape is beneficial. And I don't know whether you can see the difference. If you have paid good attention, you might do, but I'll point it out to you. The difference is right here. Yeah, so this loss landscape actually has the property that the loss doesn't kind of jump up suddenly, but it happens at the point, it still does that, but it happens at the point where it's already curving up anyway. Yeah, so if you're going and do your gradient descent, you're automatically led not to go into that area, yeah, because the minimum is here, yeah, and you're not going up towards where it might be dangerous. Okay, so if you figure out how to do a loss function that works this way, then you can do the thing you want to do. And here's some examples of our results on keyword recognition, on speech recognition, on these spiking Heidelberg digits, which, if you know the area, you can tell that this is kind of close to state of the art these days for what can be achieved. Yeah, so about 93% correct on the test set. Okay, so with that, we could go on and do continue with making harder things. So, for example, this one, it looks almost the same, but it's the spiking speech command data set. So this is from from Google, and this typical speech commands you would give helpers like Alexa and so on. And there's more words, and it's slightly harder because there's more completely different people speaking them, and it wasn't done in a sound studio, but in more realistic setting. So it's a lot harder, but you can also learn it, even though here the success rate is typically slightly lower. Yeah, and that places us with these methods here somewhere into the league table. We don't have to go through all the details. Many people have worked on these example benchmarks and have tried to push the envelope what's possible. And you can see some people actually have also advanced even further. Yeah, there's the 95% on SHD and some 80% reported now on the SSC. So things are still happening, but it's all very recent. You don't see the year here, but this table is from 2023. I started working on this in 2022, so it was a very close race of people inventing things. But that's the kind of performance. So how can we do things? And yes, we can do things. Not yet large language models. Okay, these are somewhat smaller, but we can do complicated things, and they work if we overcome these technical difficulties. But do we actually save energy? And we have shown this too. We have then ported our models onto the so-called Loihi chip. This is the chip from Intel. I showed the picture earlier. And we could say that we have enormous energy savings. Yes, some 872 times less energy used in this example compared to a Jetson or a Nano GPU. So this is an NVIDIA GPU that's used in embedded systems. So it's already a very power efficient one, but we save over and above that 872 times energy. And if we look at the energy delay product, this goes up to like 2000 times savings in energy delay product. Energy delay product is where you're not only comparing energy, but also how long it takes to compute, because there's obviously a trade-off. If you compute slower, you can actually save energy, but there's only so much slower you want to go, right? So if you look at the energy delay product, you get a bit more fair measurement of savings. Okay, that brings me to the summary. Yeah, so today's AI is based on artificial neural networks, and they use a lot of power because they have these dense computations of activations through weight matrices to get their answers. Whereas the brain has intelligence, but it uses less power partially because we're using spiking neural networks. And there are these systems developed for spiking neural networks, and we could save like a 2000 factor of energy delay product savings on the Loihi 2 chip. And the key developments here are that with we call it loss shaping method, we can use this event prop method to do fairly complex machine learning tasks. And then I didn't talk about this, but we can also do delay learning rather than learning weights, and that can be advantageous in certain circumstances. And we showed then that we can deploy on Loihi with energy savings. And the graphical summary of this technical complex problem we overcame was that is this one here, yeah, where you turn a loss landscape where you're led into a problem, a spike deletion problem, into a loss landscape where you're turned away from it by choosing a better loss function. Yeah, that's the essence of the technical advance. Okay, so that's the energy problem and some inroads to solving it that we are working on. But I wanted to end on back on the big picture and just show you a little experiment I ran a couple of years ago when ChatGPT first came out. And then I'll answer all your questions right after this. And that was this one where, and I think it's still relevant and interesting today, even though it's 2 years old, where I asked it, do you ever lie? Okay. And the answer was, well, yada, yada, yada. And then I might give incorrect or incomplete answers due to limitations in the data I have access to or misunderstandings in interpreting your question. And I thought, oh, hold on a minute. I know what's inside there, right? So this isn't, this isn't all that's happening. I was talking about the hallucinations earlier, right? So I pressed it a bit harder and I said, wouldn't you also make up things based on the stochastic sampling that underlies your generative AI algorithm? And lo and behold, there was another answer generated. And I highlighted here one part of it. Yeah, this happens because the process underlying my responses, stochastic sampling, means that I'm predicting the most likely next word or sequence based on previous context rather than always referencing factual data. Now, I would say, okay, fair enough. If you take it for just a moment as the real answer, then I'd say, well, it's never referencing a factual data. It's always stochastic sampling, but that's besides. Um, I bringing this up. I mean, first of all, it's kind of fun to see, but I'm bringing this up also because I don't know whether you've noticed, but I've just anthropomorphized the system hugely because I said, oh, it admits, I was alluding it it admits that it's stochastic sampling and oh, maybe it's not quite totally honest about it and so on. There's no such thing, right? This came about by sampling distributions of probabilities that were predicted by the artificial neural network what word should come next. And after talking about a stochastic sampling that underlies your generative AI algorithm by me here in my prompt, the word that comes next is likely to say, yes, I am sampling stochastically from a generative AI algorithm, right? So there's no admittance of something or other, and there's no such thing as a being there answering to me and admitting something or not admitting something. There is an algorithm that generates text that's likely based on what I just generated here, right? So just to end on that note, keep your thinking hat on. We have stochastic sampling algorithms, sampling from a distribution learned by text examples. We are not talking to another human or another, intelligent being, I would surmise. We're just having that algorithm that produces us some text. Okay, so don't anthropomorphize these things beyond what they are. Okay, with that warning, yeah, here's some acknowledgements to my collaborators and funders. And that's, I think, where we can start taking some questions. So, um, Isabel's there to help me, yeah. So maybe I'll start with some questions from the Q&A and then also from the chat, yeah.
That's
So
perfect. If you just go with the Q&A ones, because the one that's in the chat has also been popped helpfully into the Q&A as well. So just go from the Q&A.
perfect, perfect. So Kashyap Rajagaya, I hope that's roughly your name, is asking, is anthropomorphism something we should try to eliminate through better transparency, or do you think it's an unavoidable emergent effect of fluent language interaction? Yeah, I would say I think it's something that we need to address on the human side, yeah, by education. Basically, what I was just trying there in my last slide, um, to make people aware and educate everyone what's actually happening and what we're actually dealing with. And then hopefully that helps treating the systems for what they are. So I don't think there's much we can do in terms of the bots. Of course, you could also put a disclaimer on it and say, look, this is just generated text. Yeah, don't take it as a person. But that's easy to ignore. So I think it's all about educating people to know what they're dealing with. Um, okay. And then Yash Navani is asking, would learning with spikes change how we train neural networks compared to backpropagation? Yeah, so I'm not sure when you put the answer in relative to what I was talking about, but yes and no. Yeah, so learning with spikes for a long time, people thought had to be done with completely different ways than backpropagation, and most people agree that the brain isn't really doing backpropagation. So we have another way of learning, but no one is really understanding how it works in detail. So if today you want to do something practical and solve a machine learning problem, then backpropagation is the one method that works best. And all the big ANN systems, they are nowadays trained with backpropagation. There were times where people tried different things, but error backpropagation in the end prevailed. And we're also doing this now in spiking neural network, at least for the time being, until the time when we find out better how the brain does it, and maybe we might find other paradigms. And the issue there is, as I pointed out, that it's difficult, but it's still possible. Yeah, so the math is a bit more difficult, but it can be done with sometimes with additional tricks. Yeah, so in the end of the day, today, neuromorphic computing with spiking neural networks also is using backpropagation. That's the short answer, really. Okay. Um, then Atava Patil was asking, do you see a future where mobile devices have dedicated neuromorphic cores similar to how they have dedicated camera processors? And I would say the answer is yes. And maybe a bit more. We already have dedicated so-called neural processors in phones, but they do an artificial neural network, tensor operations. So at the moment, that's it's almost a bit like a dedicated GPU, but it's not a GPU. It's actually but they call it a neural processor, and that's the dominance of artificial neural networks at the moment. We could have these kind of other neuromorphic processors in there as well, and I think we will have them as soon as they get more established with algorithms that work well. Yeah, so coming back to our work, we need to really put the foot on the gas pedal and get this more established that we can solve real hard problems with spiking neural networks, and then people will also put the hardware in, and I think we will have it in the phone. Yeah, for sure. Then we have a question, is the level of energy use sustainable in the future? And my answer would be no, it's not. And I don't think kind of launching, I read it this morning, 1 million satellites to do computing in orbit is the answer. I mean, I think we're going off in a completely wrong direction there. The Yeah, people are arguing you could price-wise, have it cheaper than a data center on Earth, but I can't imagine this be scalable in the future. I mean, we already have problems with space crash now, so yeah, that's crazy. And then building the data centers is also crazy. I've seen pictures. There's the new data center planned. That's the size of Manhattan, and they made this illustration where you really see how big it is. It's madness. And then you build new nuclear reactors next to it to just operate that. I think is all quite wrong. So I think it's not sustainable. We need to do something different, and that's what I'm trying to advocate for, and that's why I'm trying the neuromorphic things. And I'm sure there's more mileage still than the current neuromorphic systems. Yeah, we could make systems that are even more efficient, and that's where we need to go. Okay. Do you think event-based neural networks could eventually replace traditional neural networks, or will they mainly complement them? Uh, yeah, thank you for the question. That's a very good one. I think in the short run, in the short to medium term, really, realistically, we'll always have both. Um, and But I do think there is a future where potentially we could have mostly event-based neural networks. And these paradigm shifts can happen quite quickly once you get to a point where things actually are visibly working better and where everyone can see. You go to a conference and you can just see that the results are better, people will switch and it can go quite quickly, I think. So I think eventually it will, but not next year. Yeah. At the moment, we're locked in on the artificial neural networks. Um, Now, what do SHD and SSC datasets represent in simple terms? They are keyword recognition datasets. So they are datasets where you recognize a limited number of words. So just imagine Alexa or a similar system sitting in your living room, and you can tell it, turn on the TV, turn up the heat, turn down the heat. It's kind of a limited number of these commands. And this is what these kind of benchmark data sets are testing, yeah, that you could recognize correctly these commands. That's the problem solved. Now, Nehal Thakur is asking, is the accuracy of neuromorphic computing low as its spike is low or less, creating a need for higher sensitivity of sensors? Um, if I understand the question right, it is about whether by using these event-based spiking paradigms, we also have kind of less computational ability, computational expressivity. And to an extent, yes, that's true. If I just transmit one bit, I only transmit one bit. There's no magic there that magically I can now transmit a lot of detail, a lot of information through less information, right? That doesn't work. But the essence there is that in artificial neural networks, 99.999% of what's being transmitted is actually not that relevant. And so the spiking neural networks are made to only transmit relevant information, and it's enough to be precise enough for the sensors we have or for the microphones and so on for that information to come through to make a decision. So it's a question of is it enough? It's not about maximizing necessarily information transfer. And again, in artificial neural networks, a lot of the information shuttled around in the network is completely unimportant. There are studies where they can show, they can prune away many of the connections. You just set the weights to zero after it's been trained, and it still works quite well. Yeah, so the paradigm is very kind of wasteful of transmitting a lot of information that doesn't actually work. Okay, then Jasmine Singh asked, how significant is the carbon reduction when switching from conventional CNNs to event-based models? Well, the carbon reduction goes more or less proportional to the energy used, right? So when I show 1,000 times energy less, or the energy delay product maybe is not so a direct proxy of carbon emissions because we have the delay in there as well. So let's go with the energy savings. We had a 800 times energy savings, so that would be the carbon savings we get, right? So that is substantial. Johan was asking what currently limits scaling gen and event prop to very large models? Is it memory, training stability, etc.? Yeah, it's mainly the training stability. Yeah, we are still working on other aspects. So what I can mention, for example, is the problem of gradient flow. The example I showed, I figured out how to train this network with one recurrent layer, and it works very well. And it can solve a problem appropriate for that size of network to the extent an ANN would. Yeah, so it's good. But on deeper networks, we have observed that the gradient flow, so this is the process that in backpropagation, you have the error measured at the output, but you also want to adjust weights closer to the input. If you have many layers, it's many hops away, so to speak. So the gradient needs to flow backwards and inform those weights how to change. And these gradient flows aren't as good as they should be. So with deeper networks, we still have problems. So these technical problems persist, and that's the main problem. In terms of running big networks or smaller networks, it's the same kind of resource constraints that you have with the ANNs. So if you secure a few GPUs, we can run those big networks. That's not the problem. Okay. Nehal Thakur is asking on an on the basis of the last bit, there was the example of GPT and stochastic sampling. Does this lead to the loophole that the sentence information would change the response and hence prompt engineering is important? Yeah, so yes, if I stand the question right, then you're asking about how important it is to get the prompt in the right way, so to get actually the answer you are looking for. And that's extremely important, yeah, because you need to kind of anticipate what training data might have been seen and what probabilities might be generated for new answers based on your prompt. And most of the time, there's total guesswork, of course, because we don't know how they've been trained, what data they had. So we can't have a very informed guess, but we can try to be very specific as possible to build a context where it's likely that we get the right answer. Yeah. So just to give an example, if you're interested in something where there might be ambiguity. So you might be talking about a bat, and a bat could be an animal, right? The night animal that hunts flies, but the bat is also a baseball bat, yeah, it's a sports instrument. So if you have ambiguities in your prompt, then it's a good idea to give the right context, yeah, and start talking about sports first if you mean the baseball bat, and talking about night animals if you mean the other bat. Yeah, so there's some thinking involved in prompt engineering, and at times it becomes a real art then to engineer the prompt to kind of really tease out the answers, the generated text that you really want. Yeah, so it's a whole becoming a whole science of itself. Um, then we have Palak Jain asking, what are the main technical challenges in training event-based neural networks compared to frame-based neural networks? So main technical challenge, what I already said, is the gradient flow isn't working as well. And that has to do with that, as I pointed out, especially with the method we're using, the backwards pass is also with events, right? The backward pass is also very sparse in information transfer, which also means that not so much information is flowing. It almost seems tautologist what I'm saying, but yeah, but that impedes the gradient flow, and there's problems with that. There's also these problems of the disappearing and appearing spikes that I was trying to solve even in the one-layered network. And that continues to be a problem. Yeah, so one always needs to avoid this issue, and it's not simple. And I can add the additional thing that once a spike a neuron is silent and a spike is gone and it never makes any spikes, it cannot be trained. Yeah, so spiking neural networks have this dead zone where once they get into the wrong weights, they might simply not be trainable anymore. You have to start over. So there are challenges around that as well. Now here's another question about, could the low power nature of event-based neural networks allow AI to move from massive fossil fuel dependent data centers to small solar powered edge devices? I hope so, yeah. I would hope that we can take speech recognition, for example, out of the cloud and onto everyone's device individually. There's partly solutions there, yeah, and many devices have now a kind of two-tiered system where they recognize um, simple words and things on device, and then the harder queries or when it's unclear, it's kind of shipped into the cloud. But I think in the future, these things can definitely just be on edge devices, and maybe up to small foundation models or eventually more powerful ones. I do think that should be the trend. And then it becomes more sustainable. Yeah. Also because we don't have this whole problem. I mean, everyone treats the internet as being for free, but transmitting data to America and back again to answer a ChatGPT question is also costing a lot of energy, right? So it's something to neglect. Create Shine is asking, how do probabilistic modeling, gradient descent, and the forward backward pass mechanism together contribute to learning in generative AI systems? And why do these processes make such systems susceptible to issues like hallucinations and high energy consumption? Well, okay, this question is the entire talk I was giving. But so the probabilistic modeling is not something that creates the energy problems or gradient descent. It's basically the setup of the artificial neural network, right? So the energy problems come from that having dense matrix multiplications as the paradigm that's underlying. That creates the energy problems. Whereas the stochastic modeling, the probabilistic modeling plus sampling creates the hallucinations. Now, and gradient descent simply is the one most powerful algorithm we know to make weights and neural networks do what they're supposed to do. So I don't think it's by itself necessarily a problem. And we could show that with event prop, gradient descent, and spiky neural networks is quite efficient. It's not in itself inefficient. Yeah, what makes it inefficient is the artificial neural networks paradigm underlying it. Yeah. So I think I leave that there. Yeah. So touching on many of the aspects of what I was talking about in that question. Thank you. Yeah. Then we have another one here. Are there any real-world applications today where event-based neural networks are already being used successfully? Um, yes, even though it's very edge, so to speak. So what is most successful and where we have commercial products are event-based cameras. and then sometimes also some processing that hangs on that. So event-based cameras are ones where you don't have frames and pixels in the image chip don't transmit information on this frame-based manner, but they transmit information individually based on light changes. So they just report when light changes beyond a certain threshold, and that's a fully event-based paradigm. And these event-based cameras, they're used commercially. One of the interesting ones, for example, is for train positioning, something I learned recently. And I didn't think it would be the first thing they would use it for, but they do. Yeah, they basically have these cameras mounted under train wagons, and they count the sleepers and then know exactly where the train is based on that. And it's better than GPS. So it's an interesting, yeah, interesting little application. But yeah, so these event-based cameras are coming into play. There's also some on the space station looking at other satellites. They're used for satellite tracking from the ground. So this type of stuff is taking off, but it's more on the sensor side than on the processing side at the moment. Yeah, so there's a bit of a lag there. Okay, then let's take a couple more. Should carbon efficiency become a standard evaluation metric in AI research? Oh yeah, thank you for this one. I like it a lot. I think one should start reporting that. Absolutely. And it should be a standard thing, at least to report on. If not something that one should try to improve upon, one should at least report it. It can even be improved for artificial neural networks to some extent, when you just save on the amount of the depth of your network, for example, or and the training size and so on. So that there could be a real benefit of at least putting it into the open, how much is being used. I think that would be really good. Um, are there industries currently adopting event-based AI systems? Yeah, as I said, so the train positioning people do it. For whatever reason, they found that as a really good solution. And some satellites have them. Uh, on a broad base, yeah, I mean, you also can just buy them commercially now, which is already, uh, I think, a big step forward. Yeah, so from big camera companies like Sony, rather than from some nondescript startups at a hugely inflated price. So I think that's how things are coming to kind of be serious, where they're actually becoming kind of products you buy off the shelf. You could go out and order one, today if you wanted to. So that's an interesting development. Okay. How do spiking neural networks differ computation from traditional artificial neural networks? Yes, so the computational difference is that you compute a lot of these dynamics per neuron. Yeah, so I showed differential equations for that. They eventually turned into, with a numerical solver, into an update equation where you calculate the state of a neuron. And you do that for each neuron, which can be done fully in parallel on a GPU, or it can be done completely autonomously on a neuromorphic chip for each of the neurons that are implemented on there. Um, and then only when the threshold is crossed, you need to transfer this information to all the other neurons that are connected. So that's the big computational difference. That it's kind of a per neuron computation and then an occasional per spike communication, which takes it out of this regime where a matrix multiplication with n number of neurons is an n squared operation, where you have n times n operations to do. Yeah, and you do that every time step in the artificial neural network. Here you're doing an n operation for each neuron per time step, and then occasionally the n squared one for transmitting the information. So you see that's the kind of difference. You have this intermittent transfer of information. And that saves the energy, right? It's a very simple story, really, actually, on that level. Since AI models are using more and more energy, do you think spiky neural networks are a realistic solution to this problem? Yeah, we touched on this a couple of times, and I'm just gonna say, I think it's one of the directions it might go. It's not guaranteed. There's also other ways of how people are thinking about making things more efficient, where you do artificial neural networks, but you do them more in hardware than in software. And so you might have heard of memoristas, maybe. So it's a different branch of neuromorphic computing where people are trying to do matrix vector multiplications in the chip as a hardware operation, which makes it lots more efficient. So that might be in a different way of how it might be go. It's hard to see the future, but I personally think spiking neural networks will be part of that future. Um, Good. Can renewable energy integration further enhance sustainable AI systems and how? Um, well, I do think, I mean, in the big scheme of things, lots of data centers have built solar energy and get wind energy, and that's a good thing. Yeah, rather than coal-powered power stations. I'm also not particularly fond with the new nuclear reactors with the unsolved waste problems. So I do think when this is paired together, it's at least better than the alternatives. Other than that, I'm not quite sure how that would go together. Yeah. Now, what are the ways to reduce AI hallucinations? Yeah, that's a very good one. One of the things that people are trying in the background is to combine the base algorithm that we talked about today, where you sample based on what you've learned in your weights, and combine that with some sort of fact checking. Yeah, so where once you've generated your text, you compare it against texts on the internet, yeah, by more of a search kind of algorithm to kind of back up your answers with some sort of facts. But this is a hard problem. I mean, you don't want to then just go back and be a search engine, and therefore it's not quite clear how that will actually solve it. But I do think that's one of the ways people are trying to avoid the worst problems, where it's just completely made up things that are being said. And we have already seen lots of actual problems with this. I mean, um, there's been the case, for example, of the fans of the club from Israel that who were not allowed to attend the game in the UK, and the decision was based on made up stories about them misbehaving at other games that didn't actually exist, and that was all due to AI. So the big policy decisions have been made um, based on these errors. Yeah, so there is there's a lot to work on. Um, yeah, okay, let's take a couple more. Since EventProp solves the memory bottleneck for exact gradients on GPUs, do you see Gen eventually supporting hardware in the loop training to account for physical hardware non-idealities? Or will the ecosystem remain focused on train on CUDA pipeline? Oh, thank you very much for this in detailed question. It's very good. Um, yeah, so we have plans to also do the hardware in the loop kind of training in the future, so we can go to analog neuromorphic hardware where there's a lot of problem with so-called mismatch of parameters, where the actual hardware has variability that we don't know about in training, and then often transfer fails. The transfer I showed was to low E, which is a digital chip, and it doesn't have that problem. Um, but yes, indeed. So hardware in the loop for people who might not know is a type of training where you use the actual neuromorphic hardware you will eventually want to work on for your forward pass, and then you do your backward pass on the GPU, um, and then train on that. So you get the forward variabilities of the hardware, the information about that during the training. Eventually, we also would like to actually train on chip, yeah, which would be the step even one further, yeah, where it's not hardware in the loop, but it's all on hardware. And I believe with EventProp that will be possible. And we are talking to people doing the brain scales hardware in Heidelberg and trying to work with them to do something like that. So it should be quite interesting. Okay, next one. I would like to ask for students interested in neuromorphic computing spiking networks, what skills matter most right now to learn and practice? Yeah, thank you. In my mind, it's always important to know a lot of math because if you want to really advance those algorithms, you do need to understand how event prop works, and that involves, unfortunately, quite a bit of math. And the other bit is solid programming skills because you do need to program to explore these algorithms. And even though networks like systems like Gen make things easier, it still involves programming, right? And you need to kind of develop an understanding of how to use these ecosystems, software ecosystems. So I would say math and programming are the main two skills we need for this. Mansi, Anand, how do activation functions, ReLU, GELU, sigmoid, hunch, affect conversion speed and training stability in ANNs? Okay. Um, yes, they do, but it's not an easy kind of equation where you can simply kind of deduce what will be effective or what will be fast or less effective and less fast. Most systems have now settled on ReLU simply because it's very simple and it seems to do the job. And potentially it is actually converging faster. So, and a while ago, I saw a talk where someone actually introduced the history of AI by just drawing a sigmoid, then a tanh, then a ReLU, and said, here's the history of AI. We went from sigmoids to tanh to ReLU activation functions, and that's all that happened. That's, of course, a bit tongue-in-cheek and a bit of a joke, but to some extent, it's true. We went from the more complex ones, in a sense, where people thought that was necessary, and it took a lot more computation, yeah, to the most simple ones. They seem to work the best, just at large scale. Yeah. All right. And then here, the last in the Q&A right now is loss design now a bigger bottleneck for SNNs than optimization itself, even with exact gradients? Um, yes. If I understand the question right, I think in terms of development effort, in terms of me as a researcher, or maybe you as someone who wants to try these spiking neural networks, uh, getting something to work often involves this kind of actual problem of designing the right loss. Whereas the calculation of the gradient itself, it's sorted. I mean, we've got the equations and we have actually the software doing the equations. There's no more effort to be spent on. So in a sense, yes, we moved from having to do some math to do gradient calculations to that being sorted, but now we have to still worry about making the loss a really efficient loss for our problems to actually work well. Yeah, so in that sense, maybe that's what you meant. Yeah. In that sense, the effort's now going into a different area of making the losses good for the problems you have. Okay, there's a new one. Okay, yeah. What are some active areas of research in the field of neural networks that we can pursue now as college students? Well, I'm biased here, yeah, but I would encourage you to try out these new methods, the new models, yeah. So, for example, if you wanted to get started with Gen, have a look on GitHub. It's freely available. There are tutorials that you can do as part of the documentation. You don't even need your own GPU. You can run these on the cloud and have a look what tastes. I mean, what do you find about them? Yeah, try to solve a new problem with it. I think it's all doable on the college level standard. I often give these as final year projects to our college students, so they can be done. And I find it super interesting. But as I said, I'm biased. This is my area, right? So this is the stuff I naturally find interesting. Okay, right. Super interesting questions. Thank you very much for those, and lots of them. I really enjoyed that. So yeah, thank you very much, everyone. I hope you enjoyed it too. And I'm sure there will be other occasions um, where we can have interesting sessions together and exchanges. Yeah, Isabel, any final words from you?
No, just to say thank you so much